commutative ring with a certain property.
A Boolean ring, is that the one?
No, it's number one.
No, yeah, it wants us to show that any commutative ring. Oh, that was number one, I think. The one on top.
Number one's the Boolean, number two is the one.
Yeah. So it wants us to show that any commutative ring with a set of nilpotent elements forms an ideal. And then says show for the non-commutative case that this is not true. We're showing that it doesn't imply it, not that, or are we showing that it's never true for the non-commutative?
No. All you need is one counterexample.
That's okay.
It's certainly possible for, the problem you're going to get is sums of nilpotents aren't necessarily nilpotent in the non-commutative case.
No, I was trying to prove that one.
Okay.
Thank you.
Yeah.
So I'll say this generally first, or I'm not necessarily going to assume commutative or have identity. Ideal R is a subgroup. That's all you really need. That's the subring group thing, subgroup. Let's say a left ideal is a subgroup of R that is a vacuum cleaner. It sucks, and it sucks from the left. It's the left ideal. So this is the analog. This sucking property is the analog of normal subgroup, but you need it actually from both sides.
Subgroup or subring?
Subgroups all you need. It turns out it's a subring, but all you need is this right here. Right ideal. No, actually, if it's an ideal, it's a subring. The left ideal might not be. So yeah, actually, let's correct that in the notes. In the definition, we will say it is a subgroup. Right ideal and ideal, both left and right. The subgroup part guarantees that an ideal is actually a normal subgroup of R, right? Now, before you panic too much, remember R is an abelian group, so any subgroup is normal, right? So an ideal subgroup, that gives you normal subgroup of R. This sucking from the left and the right is exactly what you need to have the analog of normal subgroups. And we'll see how that shows up later. Examples. 0 and R are ideals of R. This is a subring of R, but not necessarily it's called center of R. This is everything in R that commutes to everything else. So for example, if you want to look at the example, center of R, look at 2 by 2 matrices over the reals. Now look at the scalar matrices. That is the ones that form R times the identity. Check that that's a subring. It's not necessarily an ideal, because when you multiply it by a ring, it's no longer a scalar, or an element ring, it's no longer a scalar matrix. So here's some more. Then per F and R is an ideal. And MF and S is a subgroup. So the image of R inside of S is a subring and the kernel is an ideal. Let me prove this part at least. We know that per F and R is a subgroup. No problem there, right? Because if you just think about F is a ring homomorphism, but first and foremost, it's an abelian group homomorphism, so its kernel is a subgroup. So I've got that part of ideal there. Notice that F of Rx so this is an honest to goodness ideal, two-sided in the whole box. Example. It turns out that the ideals you can actually list these out, the ideals are. But let me start simply. What are the subgroups of R? The subgroups of R are just every multiple of a natural number or zero, right? We already know that C is a cyclic group and there's an exhaustive list of subgroups. And lucky us, these turn out to be ideals. Because when I multiply any integer times an integer that's a multiple of n, I get a new integer that's multiple n. So this is a vacuum point. All right, it sucks everything in. How about another fun example? R, the commutative of 1. Let these A's be just a collection of n elements of R. In fact, it doesn't even have to be finite. With I, this is the set of all sums AI, or this is an ideal. Let me just kind of talk you through this a little bit. If you have a sum of multiples of A, I, and another sum of multiples of AI, say sum of R prime AI, then if you add them together, you get the sum of R plus R prime times AI, right? It's just like adding vectors, vector spaces, right? And what happens if you multiply something like this by an R, an element R of the ring? Well, there's your vacuum cleaner. Right, because again, this is the sum of multiples of the ring times the AIs are often called generators, right? If n equals 1, then what's that? Oh, commutative. And actually, I'm glad you brought that up, because I bring this up because I'm going to spend most of my energy, once we get a little bit further into this, talking about commutative rings of identity. But ideals for commutative rings of identity are fairly easy, right? And it doesn't matter what side you multiply it on. It's the same thing here. I'm going to contrast this with a more general situation later. Sometimes you write it this because the ideal generated by a single element is just multiples of that element. Here is another observation that's going to help us later. The ring and R this statement that I want to make, this example is true for right ideals and two-sided ideals. Then over R, we can only one is in I. This is actually this is silly. When I go through the proof, you'll go, haha, and you will laugh at me and scoff at me and such. But it's actually a rather useful observation. Let me give you a quick proof of this. If I equals R, and 1 is in R, then 1 is in I. Right? No problem. Now, the other thing is, all you need for I to be the whole thing is for 1 to be in it. And we'll see, I'm going to do this like a left ideal. So, suppose 1 is in I, in the element of R, then R is still in I, because a left ideal is a left vacuum cleaner. So R is in I, for all R and R, so I and R is the same. Okay, any questions? Yes.
Can you go over again what principle is?
Principal just means it's generated by only one element, right? Just one element. Is that okay?
Yeah, I just wasn't sure if that's exactly.
Here is a theorem. This is very similar to kind of the subgroup criteria. Link I and R is left ideal. If and only if for all A, B, and I, R and R, we satisfy the following two conditions. an I, and two, RA is an I. Let me point out that I'm doing this little theorem here for left ideals. But you can do it for right ideals just by putting R on the other side of A, or two-sided ideals by making sure that RA and AR are both I. Everybody okay? Proof. I and R is a subgroup. Well, let me add something here. We'll say that I is not the empty set. I and R is a subgroup of R if and only if A minus B is an I. Well, AB. Okay, so that part I've got done by the subgroup criteria. Right, so let me just, so basically I've got one on the if and only if track here. So let's just see what happens with two. If I and R is a left ideal, then by the above observation, I have condition one. And then for all R and R, A and I, R, A and I. So, got it. What about the other condition? Or what about the other direction? If all A, B, and I, A minus B is in I, and RA is in I, for all R and R. Well, then again, I have that because I've got the subgroup criteria going for me. And no, all R and R, A and I, R, A and I. So it'll be left out. Let me give you a corollary. And again, so what have we done so far? We've got sort of the ideal criteria as opposed to subgroup criteria for ideals now. J and some index set, the family of left ideals. Then the intersection this is a theorem we have from group theory. The analog is true here. And I'm going to use this to sort of build back this sort of generating, this idea of a generating set here. But let me, let's deal with corollary real quick here. Okay, so what have I got? I've got this big collection of ideals. We know we know that the intersection of all these, in fact, is a subgroup. Right, because we've already had that here, because remember, this collection of left ideals is actually a collection of subgroups. So their intersection is still a subgroup, so I've got that taken care of. Call it something here. Let's call this B, so I'm right there, so it's all the time. Now, so R is in R. And alpha is in B. Then for all J in the index set, alpha is in I J. Therefore, for all J in the index set, R alpha is in I J. Because after all, each of these R alphas is a left ideal. Therefore, R alpha is in, this will be as a left ideal. Again, just like before, I can replace the word in this corollary left with right, or just remove it and call it non-equal. Questions so far? Okay. Let me give you a definition. I'm gonna follow this up with some marks. And again, with this, you get a similar such thing proves an X and R a subset. No structure here, just some collection of elements in R. But I J in some index set. The collection of ideals. Again, you can put left, right, or two-sided. Either collection of left ideals containing set X. Right? So what you do is you just gather together all the left ideals on the ring, maybe set X. There's at least one of them, R itself, right? But you gather all these together and you find the left ideal of R generated by X. So in other words, it's sort of, so the ideal generator, the left ideal generated by some set X is just the smallest ideal ring that contains the entirety of the set X. So it's just the intersection of all ideals that contain this. Now, let me make a mark here. Throw this in here. So remarks to the definition. Put them all in here. One. Here. Let me call this. Let me call this I. This intersection. Just for notation purposes. If X is finite, then I is finite in general. So if I say that an ideal is finite in general, that means that it's generating oil has a generating set that consists of 5 many elements. 2, if x is 1, then principal. We already talked a little bit about principal ideals in that example here, but let me remind you, in that example, the ring was commutative with identity. Here, we make no such distinction. Anything that can be generated by a single element is a principal ideal here. A principal ideal ring is a ring where every ideal is principal. And 4, or maybe I should say 3b, a principal ideal domain, PID, is a ring, is a PIR. So a PID is a PIR, but I'm assuming that the ring is commutative with identity and no non-zero zero values. Anybody give me an example of a PID? I want to see how smart aleck you can be. Z, right? We've already seen that example. Every ideal is generated by n, right? I can give you another example. Any field, right? Any field is a principal ideal domain because the only ideals are 0 and 1, right? Or generated by 0 and the whole ring. There are many other examples of PIDs. Let me ask you one more question. Going back to definition 5.2.8, what if the subset of R is the empty set? What's the ideal generated by the empty set? 0. It's a 0 ideal because every ideal as a set contains the empty set. So this is the intersection of all ideals. But 0 is an ideal that is contained in every ideal, so it's a 0 ideal. Okay. I want to give you a theorem to illustrate the evil world of rings that are not commutative, and especially rings that don't have identity. So before I do this, let me remind you, if I have a PID, so let's suppose then any I and R with a form Rx. So X. And of course, this is the set of just multiples of X. So if you live in the world of a PID, then if I pick an ideal out at random, then I can find an element in that ideal X that generates everything. So everything is a multiple of what's in there. Great. There. This theorem will go a long way to justifying our research area. Let R be a ring. And X, R, put A, B, and R. Principal ideal. Okay. And when I say principal ideal, I do mean ideal, right? I mean two-sided. What kind of elements? What do you expect to live in this ideal? Well, it's got to be a vacuum cleaner and it's got to suck from both sides, right? So you've got to have elements of this form, right? It's got to suck from the left. You've got to have elements of this. It's got to suck from both the left and the right. So you've got to have elements of this form. Well, actually. So you have to have elements of this form, and this form, and we have to sum these up. And I'm still not done. What else might be? You also have to have where R double prime, R triple prime, R, and then an integer. Right? Because the smallest ideal that contains A has to contain stuff that looks like this. And I don't need sums here because if I add up several RAs with the R's on the left, I can pull it out like it's a single element. Agreed? It can also contain elements that look like this. But if I write several elements with some with the R on the right, I can pull that out and write it this way. I also need this, right? Because I need it to suck in from both sides, right? And here I can't necessarily pull stuff in because on the right and on the left, right? What's this all about? Why do I need integer times A? What's that? It is taking into consideration the terrible fact that the ring may not have identity. I mean, for sure, the ideal generated by A better contain A. Agreed? If you leave that out, show me how you can make A. There's no guaranteed way of making A because this R may not ever be 1, or this R, or any of these. You have to do this just to make sure that A and A plus A and A plus A plus A and so forth is in there. I mean, convince me that this doesn't suck, and I'll give you $100, right? Because it totally does, right? This is awful.
Of course it does.
Yeah, I mean, look at what principal ideals look like here, right? Look at what an unholy mess this is. So,
So we're supposed to.
That was a good joke.
so let me work on this a little bit. Yeah. Then I can make this much better if R has one. If I notice, this gets rid of everything except this term here, which I would expect anyway. The reason why I can do it if R has one is now I can pretend that's RA1, and that's 1AR, right? And this is, well, N's in there, one's in there, this is 1A1. So these all can be put into the sum, right? So if you have identity, bang, it collapses to this, which still is bad, but it's better. Number B, yeah, A is in the center of R. Now remember, what this means is A commutes with everything. Then what happens now? Well, if A is in the center of R, I can put all my R's on the left with impunity, right? Because I can move the A's and the R's back and forth freely. So I can put this one over here and I can group them all together. So the RA takes care of this, and this, because I can move the A and make sure that all the R's are on the left, but it still doesn't take care of this. And finally, if you look at RA, yeah, I don't know what this is. C. RA, this is the set of RA by definition. This is a left ideal. Because if I had R1A plus R2A, well, yeah, it's all R2A. And clearly, if I multiply on the left by anything, because the ring is multiplicably closed, I still get something in this form. Which may not contain A. Because again, if there's no identity in here, there's no guarantee you get an A out of this. But, you know, number D, if A is in the center of R and R has an identity, then the ideal generated by A equals RA equals AR. And finally, just to kind of make it clear right here, if A1, A2, AN are in the center of R, and we have an identity, then the ideal generated by the set of elements A1 up to AN is exactly what we Any questions? So anyway, if nothing else, I hope this little theorem convinces you. We kind of talked our way through it, but I hope this theorem convinces you that this is why having an identity, especially I think the identity is the one that sort of drops the most terms down, is important. As is important that it's community, right? Or it just life is a lot easier in those cases. Any questions? Okay, so now we're going to start to do, here's some basics of what we need. We want to look at the algebra of ideals. In other words, how do they perform? The ideals themselves have a structure where you can add them and you can multiply them. Let I and J and R be left ideals. We define I'm going to define this new, I hope it's going to be a left ideal, I plus J, just by taking I and J, the left ideal, putting them together. What's this going to be? Well, we have some familiarity with this because this is like, we've done this with abelian groups. If I have two abelian groups A and B, then their sum is just collections of sums here. This is a group, we've seen this before, and it sucks from the left because if I multiply any one of these sums by an R, this is RA plus RB, right? And RA is an I because it's left ideal, and RB is in J. So this is actually left ideal. What do you hope for here? How do you hope this is defined? I know what I'm hoping for. I hope it's not going to work though. Does anybody know why? I mean, I wish this was just like sums, right? I wish you go, okay, IJ, that's going to be something in I times something in J. There's my left idea.
Just guaranteed to end up with something.
Well, so that's right, actually. And it turns out,
I mean, something in J.
actually, that's an astute observation. And that is, if J is indeed a left ideal, this is actually contained in J, isn't it? Right? And if I is also a right ideal, it's contained in I as well, right? Well, here we're talking about left ideals. The problem here is if I have here's the problem. What if I have A1, B1 and A2, B2, right? Where the A's are in I and the B's are in J. What happens? After all, these are an ideal, so I've got to be able to add these up, and I have to be able to rewrite this as X times Y, where this is an I and this is an J. There's no guarantee I can do that. In fact, I can give you many examples where you can't. So how do you fix this? Well, in ring theory, here's how you fix it. Put a freaking sigma in front of it, just add stuff up, because now it's going to work. Right, because now what happens is if you have a sum of things, first term in I and second term in J, and you add another sum of those things, what do you get? You just get a bigger sum, which is still like that, right? That's the good thing about the two binary operations, you get around it. But this is really the best way to define I times J. So let's give you a theorem here. Algebra of these things. A1, A2, up to AN, and A to C, all be left ideals. Again, as with all these theorems, I'm going to replace left with right or two-sided. A are left ideal. And these are both defined inductively, right? I only define sums of two and products of two, but just go by induction. B, A plus this left ideal, same as this one. You also get associativity, that is to say, this ideal is the same as this ideal. And I'm going to use a summation notation for this. And somewhere on both sides. Okay, you might ask yourself, what happens when you mix and match, right? What happens if some of these are left ideals, right ideals? Sometimes it works, sometimes it doesn't. Okay, any questions? Any questions out there? All right, well, you all have a good one. If there are any questions, and we will see y'all next time.